we would like to present you our final project, solving graph coloring problem using MCDS. Our team consists of 5 people. That's Sergey, our mastermind, Maxim, Nikita, that's me, Nikolai, and Gleb. So let's start. Here is the plan of our presentation. First, I'm going to say some introductory words. After that, I'm going to state the problem. And then Maxim, Gleb, and Nikolai will give a review on some algorithms that can be used to solve our problem. And Sergey will end the presentation with experiments and results. Let's start. Imagine you have a graph which has a set of nodes and set of edges, and we want to assign each node a color such that 2 adjacent nodes have different colors. It's a very hard problem, and it can be used in building circuits or making schedules, but exact algorithms work pretty bad because they do not scale well. And when a graph has 100 or more nodes, they work bad. So that's why stochastic algorithms work better, and a great candidate to solve this problem is MCDS. Let's rigorously define the problem. We have a graph G, which has a set of vertices V and set of edges E. We want to find the set of colors of minimal size such that each vertex has a color and its neighbors have different colors. But also this problem can be redefined as a planning problem. Indeed, we have a state space, which is current assigned colors. We have an action space. It's possible colorings of vertices. And we have a state transition function. And initially, we have an uncolored graph, and the state we want to come to is when the graph is fully colored. The cost we assign is the negative number of colors, so the less colors we use, the bigger the reward. And our goal is to get an optimal policy which maximizes the reward. Now, Nikolai with the review of algorithms.
Okay, so we have 3 types of classical algorithms that can be used. Greedy algorithms, which I will talk about it a little bit later, but it states for colors nodes with the first available color. Tabucol algorithm, which states for tabu search and plus approximation of chromatic number. So the chromatic number is the smallest number of colors needed to color the vertices, so that no 2 adjacent vertices share the same color. And tabu search, it's the meta-heuristic search method employing local search methods used for mathematical optimization of problem. So local searches take a potential solution to a problem and checks its immediate neighbors, so in a hope of finding an improved solution. But local search can stuck in the suboptimal regions or on the plateaus. So the tabu search improves the performance of local searches by allowing make versus move, and it helps us to not stay on the plateau and move on. And as well, it discourages the search from coming back to previous visited solution twice. As well, we can translate our graph coloring problem to another programs. So like we can implement the integer linear programming or Boolean satisfiability problem solvers. So the greedy algorithms, why don't we use the greedy algorithms just it? So from one hand, the vertices of any graph can be always ordered in such way that the greedy algorithm will give the optimal coloring. So we just, first of all, renumber the vertices from the smallest set of equally colored vertices, and then we do the same with the second largest set and the third largest set, and so on and on. And we apply the greedy algorithms with such order of vertices, and then we obtain coloring. The obtained coloring will be optimal. But the main problem is that to do so, we have to, we get NP complete problem. So the heuristics algorithms are used in this case.
So let's consider Monte Carlot research-like algorithms. At the beginning, we consider the first main algorithm that we will use in the future. The first is nested Monte Carlo search. The main idea is that the policy remain the same for the execution of the algorithm. However, in the nested rollout policy adaptation algorithm, the policy is learning during the search. So let's consider another algorithm that we can use. Next slide, please. The first algorithm is playout algorithm. The idea is simple. We use the policy to choose the probability of choosing the next move, and when we count it, we can use the next action. But this algorithm is very simple, and we want to find some more stable, which can give us the solution fast. So let's consider the next algorithm. It's an NCP. As I said before, here the policy remained the same from the execution, and at each step and for each move, we evaluate its score by completing the partial solution using the solution from our policy. Let's think about how we can improve it, and we can consider the next algorithm, which will be considered by Maxim.
So the nested rollout policy adaptation algorithm is highly inspired by nested Monte Carlo, as said previously. As an NMC, each level of the algorithm calls a lower level, and each level returns the best score and best playout sequence found at this current level. But there are two main differences. First one is that the playout or rollout is no more a standard Monte Carlo, but is based on the learned policy. And the second one is that not all decision may not be explored, and this is depending on the policy-based sampling. So speaking more about the adaptation function that is used in previous algorithm, first of all, we choose for each decision in the playout sequence, we increase the probability of the best decision, and then compute the normalization factor and use this in the updating policy using exponential moving average, for example. So next, please. So comparing those two algorithms, we can check the number of hyperparameters in NMC, as the main hyperparameter is depth, and for NRPA there are several important ones. Those are depth, iterations per number of iterations of playout, and the learning rate. So NRPA has quite a few hyperparameters and requires some kind of research.
So, and we have some type of hyperparameter is the action space, because in vanilla version, as far as it's been said on the statement of graph coloring problem as a planning problem, the next action is basically coloring the vertex. So we do have all the uncolored vertices and all the colors we can apply to them. So in the worst case, the number of actions is the power of the number of vertices V times number of variable colors C. So in the worst case, it will be like, for us, it will be 400. For the synthetic dataset that we will talk a little bit about later. And so this is a lot, and we need to somehow reduce number of actions, and we follow the policy that was proposed in the cited paper number 2. We pick only one vertex, and so the actions will be available colors that we can color up this vertex. So in the worst case for us, it will be less than 10. So we have an ability, previous slide please. So we have an ability to pick the vertex randomly, or we can pick vertex by minimal available number of colors, and that's the policy that was used inside the paper. And we can pick vertex by maximal vertex degree, and this policy is usually used in sorted greedy algorithm. So next slide. So experiments, we've used testing on generated graphs that we do no Hermite number for them also. And we compare our NMCS and NRPA with typical and greedy algorithms. So next slide. Here's our main experimental table. We've tested on synthetic data with 40 to 60 number of vertices, and another data set with 35 to 35 number of vertices. And both of these data sets have graphs with Hermetic number from 3 to 8. And so then, as far as you can see by the numbers, we've reported, since the typical actually was the best, then we decided to report not the error with respect to real Hermetic number of graph, but with respect to typical found solution. So as far as you can see, NRPA and NMCS work pretty good for the big data set with 40 to 60 number of vertices. But NRPA works a lot worse for the smaller data set with 35 to 60 to 45 number of vertices. And the greedy is like the worst. And so NMCS is actually better than NRPA. And for NMCS, you can see that node, but ordering by degree of node is better than SATU1. And yeah, it really performs very poorly. So next slide. We've talked about hyperparameters, and we've experimented a little bit with NMCS hyperparameter depth. And yeah, as far as you can expect, with increase of depth, the result increases too. But there another very interesting property that sometimes with increase of depth for algorithm, we can get worse results. And we think that this is connected, like this, that this is connected with the way we choose actions. And so we will try to elaborate that a little bit in the future work. So next slide. And so conclusions, NMCS showed itself quite promising, but we need more testing. For NMCS, degree ordering showed itself better than SATU1. NRPA showed itself pretty bad, but still we haven't searched hyperparameters for it. So maybe this is because of hyperparameters tuning. And all the methods are worse than typical, but a lot better than greedy. So that's something. And also we have to research the action space. So next slide, future work. Yeah, as far as we said, we have to research hyperparameters a lot. And we have to research the way we choose actions. And also we can use various heuristics for playout algorithm, both deterministic and stochastic ones. For example, greedy or even ILP or SAT solvers. Yeah, so that's all. Thank you for listening. And
We're ready to
GitHub.
answer your questions. Thank you.